Well, greetings everybody. I would like to look at this problem, which I think you will find on your assignment on MyMathLab. And I think it seems a little more complicated than it actually is, except perhaps for this last part. It has parts A, B, and C. But let's look at it. We'll go through it. What I'm given is a quadratic function, meaning a parabola on a graph or an equation that looks like that relates how the airspeed of a plane affects its fuel use, okay? And on the vertical axis, it says miles per pound of fuel use, okay? Or miles per pound of fuel. And that's a measurement of how efficiently the plane uses fuel, okay? Now, we might think in cars like that your fuel efficiency is in miles per gallons, but in airplanes, we would measure the fuel in pounds because the weight of the plane is important. So I see that, like, if the plane is, around 70, 80 miles an hour, my fuel use is much less efficient than if I'm at this peak here, which looks like it occurs at about 100 miles an hour. But then if I go beyond that, say 120 miles an hour, I'm looking at this point or somewhere around here. So I'm seeing that, like, it looks like the most efficiently the plane uses fuel is about right there, where it looks like the plane will get about 1.3 miles per pound of fuel at the best, okay? As opposed to right here, 1 mile per pound of fuel. What would be better if the plane got 1.3 miles for every pound of fuel that it used, or if it was over here where at 1 or 0.8 miles per pound of fuel? Obviously, like, that point at the top is the most efficient, okay? So in parts A and B, it says to look at the graph and use this formula, which is given, that is a measurement of how efficiently the plane uses fuel based on its airspeed. Look at that equation right there. How we would use that equation is we would put A, the airspeed, into it and do our calculations. Negative 0.000651 airspeed squared plus 0.129 times airspeed minus 5.07. And we do all those calculations, and the answer we get is M, the fuel use in miles per pound of fuel. That's the way that formula is used. So for parts A and B, I've combined them a little bit. If we can agree that that vertex point represents the most efficient airspeed and best use of fuel for the airplane, then to tell you the most economical speed would just be a matter of figuring out where that point is. So like part A or B, like it says, look at the graph and see if you can figure it out. Where does it look like that point is? What is the most economical airspeed? It looks like it's right there at about 100 miles an hour. Okay, just, from best estimate on the graph, that looks where to be the vertex is. Okay? All right, so that's why the answer to part A is 100 miles an hour. Most efficient airspeed, where at that speed you're going to get about 1.3 miles for every pound of fuel, which is much better than any other points on the graph. We could also calculate that vertex directly. I can see it on the graph. I mean, I can roughly tell where it is, but it would be way more precise to calculate it. So do you remember how we figure out where the vertex is? Well, we find the x-coordinate of the vertex by negative b over 2a, okay? So in that formula right there, m, miles per pound of fuel, is negative 0.000651 airspeed squared. That whole formula, we could find the vertex from that, where a is this number, b is this number, and c is that one. We can use our formula, negative b over 2a. Okay, so I do negative, b is 0.129, okay, divide by 2a, a is negative 0.000651. So I do these calculations with my calculator and I get 99.07834 miles per hour. So the x coordinate where on our graph, we really don't have X and Y. We have for X airspeed and for Y miles per pound of fuel. Me finding the X coordinate is finding the airspeed at that vertex point. So that is the most economical airspeed. Okay. Do I need to find the Y coordinate of the vertex? Well, it didn't ask me. It just says, what's the most economical airspeed? And that's just the X coordinate of that vertex point. Okay. So we can do it two ways. We can look at the graph. We see it looks like it's about 100 miles an hour, as best we can tell from looking. Or we can calculate the X coordinate of the vertex point, and we do that. We get 99.08 miles per hour, rounding to 2 decimal places according to these instructions. Okay, so that's how we can have two different tactics for finding the most economical, the most efficient airspeed based on either looking at the graph or doing our calculations, all considering that this is a quadratic function. It's a parabola, and all the formulas we learned about for parabolas apply to it. Now let's look at this last part in a little more detail. It says this, it's somewhat hypothetical, but we'll take it as it is. If the aircraft was flown at 99 miles per hour and got 1.3 miles for every pound of fuel, okay, so that's the rate that it uses fuel at that speed, and the fuel weighs 6.06 pounds per gallon, the number of gallons of fuel that were burned per hour would have been, okay, so we need to find that number. I need to go from knowing how fast it's going, how fast it burns fuel in miles per pound, to figure out how many gallons per hour it's burning fuel. So what that comes down to is I'm converting between a lot of different measurements. Now I'm going to pan away from this, and I'm going to show you how I would conceive of this question. So I have that the speed is 99 miles per hour. And at that speed, the fuel use is 1.3 miles per pound of fuel. And what I want is to figure out the rate it's burning fuel in gallons per hour. So it's a matter of converting 1.3 miles per pound of fuel to question mark gallons per hour, where that question mark is my answer, my conversion, and the number that I'm looking for. Okay, so here's how we do that. The technique is called dimensional analysis. Okay, and if you've ever taken a science class that relies on measurements, you've learned dimensional analysis. So if you've ever taken chemistry or physics, then you've learned some dimensional analysis. Now, if you haven't, then I'll show you in this video, okay? I'll show you enough to know how to do this kind of problem. So I'm going to start with the measurement that I'm working with, 1.3 miles per pound of fuel, okay? That's how fast in terms of mile per pounds of fuel that the plane uses the fuel. It travels 1.3 miles. It uses a pound of fuel. That's what that means. Okay, so I start by writing that down. And I want to cancel the units I don't want and introduce the units I do want. So we can go about it like this. If I multiply this by the fact that the fuel weighs 6.06 pounds per gallon, and that was given to me, if I go back up and read that question that was given, then what that will do is it will cancel pounds out of my work. And then if I multiply the fact that the plane was going 99 miles per hour, which I write this way, I wrote miles on the bottom because I want to cancel miles out of it. I want to end up with gallons and hours. I got to cancel miles and pounds out of it. So this number was just given as the speed. I could say the plane was moving 99 miles per hour, or I could say for every 1 hour it traveled 99 miles. It doesn't matter how I write that. Okay, so I put a note here. We can always turn our units upside down if we need to. So for example, I could say 12 inches is 1 foot, 12 inches per foot, or I could say 1 foot per 12 inches. Or I can even divide 1 by 12 and say That's 0.083 feet per inch. 1 inch is 0.083 feet. So I can do that. The reason why I put the speed this way is with miles on the bottom, I cancel miles on the top. Okay? And what am I left with? What units of measurement am I left with? Am I left with gallons and hours like I wanted to? I started with miles and pounds of fuel. I used all the other measurements I was given, and I wrote them there and multiplied them in a way that I canceled the ones I didn't want, and I have hours, okay, and I have gallons. So that seems to be maybe my answer. Let's see. As far as the numbers go, we got to multiply those. 1.3 times 6.06, and I got hours on the top, and then I got 1, and 99 on the bottom, and gallons on the bottom. Okay? Now, all right, so is this my answer? Sort of. I wanted gallons and hours, I have it. But look at this. I got hours on the top, gallons on the bottom. Okay? All right, so can I fix that? Remember, I can turn any of these upside down if I want to. Like right here, I could have written the airspeed as 99 miles on top and 1 hour on the bottom. 99 miles per hour. But if I need to, I can write it 1 hour per 99 miles. 1 hour goes by on the clock, the plane travels 99 miles. Same way, it doesn't matter. So this is upside down. But that's okay. I'll flip it to gallons on the top, hours on the bottom. All right, so I got 99 gallons. I moved this on the top, and I got 1.3 times 6.06 hours on the bottom. And if you take 99 and divide by 1.3 times 6.06, you'll get 12.567 gallons on top, hours on the bottom. So that's how fast, in terms of time, that the plane burns fuel. Okay? I went from knowing how fast in terms of pounds that the plane burns fuel, 1.3 miles for every pound of fuel, to how fast the plane burns fuel in terms of gallons per hour. All right? And that's what I wanted. So let's look back up here, 12.567, okay. Is that the answer? 12.57. Yes, if you round to 2 decimal places, it is 12.57 gallons per hour. All right. Okay. So this is called dimensional analysis. It's how we convert from some measurement that we have to some other measurement we want. We just write our additional information in a way that we cancel the measurements we don't want to be there, and we introduce the ones that we do. Okay, now if you understand dimensional analysis, if you've seen it before, then maybe you're good with this. But I thought for those of you who don't recognize this or have never seen it, I'd show you a few more examples. Okay? All right, so if you want to see some more examples, here we go. So I want to show you some examples that allow you to get a better feel for what you just saw over there and maybe bring a little more understanding to it. So how about this one? Can we convert 100 miles an hour to so many feet per second? How many feet per second is 100 miles an hour? Like, can we convert that on paper? I know I could type it into the Google or something and ask, but I want to know, how do you do that since we're learning math? I remember when I was younger, I played baseball, and I tried to figure out how fast I pitched. And I measured the feet, all right, from the pitching mound to the home plate, and I tried to get somebody to measure the time in seconds. And then I so badly wanted to convert that to miles per hour, but I figured it out. The only problem was it's very hard with like a stopwatch, the time, the length of time a baseball takes to get from the pitcher's mound to home plate. All right. But nonetheless, can we do this? All right, so let's do it the same way. I have miles and hours. I want to cancel miles and introduce feet, and I want to cancel hours and introduce seconds. So here's how I can do it. So let's do this way. All right. So how can I introduce miles into this and maybe equate it to feet? So it's a matter of fact that 5280 feet is 1 mile. They're the same thing, okay? So I could do like this. I could write a fraction, multiply it, and put 1 mile down here and 5280 feet here. And that's a true statement. Every one of these fractions I write is like an equation. 1 mile is the same thing as 5,280 feet. Okay? And when I was over here doing this, these were all true for my situation. For that plane, 1.3 miles was the same thing as 1 pound of fuel, in the sense that the plane used a pound of fuel for every 1.3 miles it traveled. So here, this right here is a true statement. It happens to be that 1 mile is 5,280 feet. Why would I write this in there that way? Well, because it's going to allow me to cancel miles out of this. I want miles gone and I want to introduce feet, and this will do it if I multiply in this way. If I stopped here and multiplied these numbers together, I will have converted my speed, 100 miles an hour, to feet per hour. But I want feet per second. So think about it like this. Can we cancel hours and introduce seconds? If you know the conversion between the two of them, you can. And it happens to be that there's 3,600 feet, or sorry, 3,600 seconds in 1 hour. Okay? Those are the same things. An hour of time is the same thing as 3,600 seconds. So that's what I need. I guess the question is, how do I write it? All right? So think of it like this. Do I put 3,600 seconds up here and 1 hour down here? Because I could if I wanted to. Those two things are the same. 1 hour is the same thing as 3,600 seconds. But would that cancel the units I have here and introduce the new ones in the way that I wanted? No, it wouldn't, because like hours on the bottom is not going to cancel the other hours on the bottom. Okay, so this might be true, and you could write that down if you needed to, but it's not applicable here if I want to convert to feet per second. So I'll just turn it around the other way. It doesn't matter which upside down, right side up you write these. So I want to do 1 hour, because I got hours on top canceling hours on the bottom, 3,600 seconds. Okay, and then that will do it, because now I got this canceling that. And what am I left with? After I cancel miles over miles and hours over hours, what am I left with? 100, 5280 feet on top, 3,600 seconds on the bottom. I get feet per second. Feet on top, seconds on the bottom. Okay, so let's collect our numbers. I would get 100, 5280, and I get feet, and all that's over 3,600 seconds. Okay, and then let's get that number with our calculator, see what it is. So 100 times 5280 divided by 3,600, so that turns out to be 146.7 with a little bit of rounding. Okay, 146.7 what? Feet per second. So if something is moving 100 miles for every hour of time that goes by, it's also moving 146.7 feet for every second that goes by. Okay? We just converted one thing to another. Now, the way I thought about this, the way I chose to write down every fraction with the associated measurements in it, is exactly how I would have considered doing it over here. I wanted to cancel the units that I don't want to be there and introduce the ones that I do. And whether I write these upside down or right side up is just a matter of how I need it to be. Okay, so let's do one more, just in case. Why not? So let's see. Let's do this one where this is not really a hypothetical situation. We could have this. We have a metal bar that, let's say, it weighs 3 pounds per foot. So doesn't matter how long the bar is, but so suppose like maybe a factory produces this kind of metal bar. Maybe it's used in construction or something, and we know that every foot of the bar weighs 3 pounds. So if the bar was 2 feet, it would weigh 6 pounds. But we're just saying its weight can be expressed as 3 pounds per foot. Can you convert this to inches per ounce? Okay, we could do that the same way, right? We could do it exactly the same way. So we would just have to cancel pounds and introduce ounces, and cancel feet and introduce inches. So doesn't matter where you start on that. Let's start with feet. Can you cancel feet and introduce inches? So I could say 1 foot is the same thing as 12 inches. And that's a true statement. This is an equation. This fraction here says that 1 foot is the same thing as 12 inches. But if I do it like that, I'll cancel feet, okay, and I'll get inches. All right. And I want inches in my answer. Now, maybe I don't have it quite in the right place yet, but I'll get there, right? Okay, so now what about pounds and ounces? How do I cancel the pounds and get ounces instead? Is there a relationship in terms of weight between pounds and ounces? And there is. We could look that up if we need to. It turns out that 1 pound is the same thing as 16 ounces. So if I had it like that, would it do what I want? Would it cancel the pounds and introduce the ounces? Well, it might be true that 1 pound is the same thing as 16 ounces, but once again, I've got it backwards. I need to write it the way that allows me to cancel what I don't want to be there and introduce what I do. So I need to do like this. I make mistakes for dramatic effect sometimes, and that was one of them. I need it like this. 1 pound is 16 ounces. Okay, yeah, because like the pounds down here would cancel it up there. That's the way dimensional analysis is done. Now what am I left with? I canceled pounds over pounds, feet over feet. I got ounces over inches, and those are the units that I want to be there. All right, so let's collect all this. I've got 3 times 16 on top, and my measurement up there is ounces, and I got 12 inches on the bottom. Got the number 12 and a unit of measurement, inches, left over. Okay, so let's see, what do I get out of that? I got 3 times 16 divided by 12, so that's going to be 4. So I got 4 ounces per inch. Okay, so it's like what that tells us is every 1 inch of that bar, of that metal bar, weighs 4 ounces. Okay, or for every 4 ounces of the bar, there's an inch of length. But that's not quite what I wanted. I mean, the problem was, for whatever the reason, to convert it to inches per ounce. But can't you turn these upside down? Like, I mean, you could say there's 4 ounces per inch of bar, but you could say, turn upside down, you'll get 1 inch per 4 ounces. It's the same statement, really, just saying it the other way. Inches per ounce. Now I'll do one more thing that we would typically do in order to fully express our conversion. Yes, on this metal bar, for every inch of it, there's 4 ounces of weight. But I could also just divide these numbers. If I divide 1 by 4, okay, then I'll get 0.25 inches over ounces. Okay, so it's like saying for every 1/4 of an inch of the bar, there's 1 ounce of weight. So that's the kind of expression that we're looking for in that conversion. All right, a 1/4 inch of the bar 1 ounce of weight. Same thing as saying 1 inch of the bar, 4 ounces of weight. We can turn the measurements around, we can divide the numbers. Those are all the kinds of things we can do when we do dimensional analysis. So I really did try to think of a few examples that would shed a little more light on what I did over here if you've never seen it. But how about, if you came across this problem and it was expressed the same way with the same information but maybe different numbers, you could still just proceed exactly in that fashion and not question it a whole bunch. And maybe you could start there and then maybe look at the other examples if you wanted to understand it a little better.